Welcome to the session on differentiation, modelling with differentiation. The objectives for this session are to model real-life situations with differentiation. Let's begin by looking at the rate of change. The rate of change of y with respect to x is represented by dy dx, or small change in y over small change in x. Let's take a look at an example. The surface area a centimeters squared of an expanding sphere of radius r centimeters is a equals 4 pi r squared. Find the rate of change of the area with respect to the radius. Let's try solving this. Now the surface area a equals 4 pi r squared. As given in the question. Therefore, if we differentiate this with respect to r, we obtain dA dr equals 8 pi r. And this is the rate of change of the area with respect to the radius. Let's take a look at another example. Suppose that you have an expanding cylinder with radius r and height 2r. Find the rate of change of the volume V with respect to r at the instant when r is equal to 3. Let's try solving this. The volume of the cylinder is V equals pi r squared, in other words the area of the base, multiplied by the height. So here's the height, 2r, and if we tidy up, we obtain 2 pi r cubed. So therefore we have that the volume is equal to 2 pi r cubed. And therefore if we differentiate, we obtain 6 pi r squared. Now when r is equal to 3, dV dr, which is equal to 6 pi r squared, becomes 6 pi 3 squared, because we're substituting r equals 3 into the formula. And this gives us 54 pi. Now let's take a look at another example. A water tank is to be made into a cuboid from 60 meters squared of sheet metal. The tank will have a horizontal base but no top. The width of the tank is x meters and its base is a square. Firstly, find the volume V meters cubed of the tank. Secondly, find the maximum or minimum value of V, given that x can vary. And finally, explain why the value of V you have found is a maximum. So let's solve part A first. Find the volume V meters cubed of the tank in terms of x. The volume equals the area of the base times the perpendicular height. Let y equal the height, as shown in the diagram. The area of base equals x squared, as shown here. And the area of each rectangle equals x times y. Here, 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 and here. Now the surface area of the tank is equal to 60 meters squared. This is part of the question. We can also express the surface area of the tank in terms of the four sides on the side and the base. So here's the area of the base, which is x squared. And since the area of each rectangle on the sides is x times y, we have that the surface area of the tank is also composed of 4 of these side areas. So 4 times xy. Here, 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 and here. And of course, the entire surface area of the tank is equal to these 4 sides plus the base. So we have this equation that we can now rearrange. The equation 60 equals 4xy plus x squared rearranged becomes y equals 60 minus x squared, all divided by 4x. And this equals 15x inverse minus x over 4. And therefore, the volume, which remember was equal to the area of the base times the perpendicular height, is now equal to x squared times this value of y. And it's not actually a value, it's an expression for y. And here's the area of the base. And tidying this expression up gives us 15x minus x cubed over 4. Now let's have a go at part B. We are required to find the maximum or minimum value of v given that x can vary. So remember from part A we had that v equals 15x minus x cubed over 4. If we differentiate this, we can now proceed to try and find a maximum or minimum value. So differentiating gives us this expression for dv dx. And of course the stationary points occur when dv dx equals 0. So we are therefore required to find x when 15 minus 3 over 4 x squared is equal to 0. And so solving for x gives us x equals plus or minus the square root of 20, which equals plus or minus 2 root 5. Now since x is greater than 0, because we're looking at area and remember x is a side length, x has to be equal to 2 root 5, not minus 2 root 5. And therefore, plugging this value back into the formula for v gives us that v equals 20 root 5. And this is either a maximum or a minimum value of v. And finally, let's solve example 3c. We are required to explain why the value we have found for v is a maximum. So let's solve this. From part B, the maximum or minimum value occurs at x equals 2 root 5 and v equals 20 root 5. In part B, we also found that dv dx equals 15 minus 3 over 4 x squared. So if we differentiate this again, we obtain d2v dx squared equals minus 1.5x. And of course, this is less than 0 when x equals 2 root 5. Now, since d2v dx squared is less than 0, we can therefore conclude that v equals 20 root 5 is the maximum value of v. This brings us to the end of this session. If you have understood its contents, you should be able to model real-life situations with differentiation. Thank you very much for listening. To understand this topic in greater depth, do attempt the exercises in your textbook related to this topic.